Good evening. Today we'll be talking about some basic driver operator math. We're going to do a little bit each time because math is boring, so we're not going to do overload levels of math. First of all, why do we need to know the math? There's pump charts and phone apps and all this other stuff. Well, we'll get into that. We'll also get into some constants that are needed for these equations. And then we'll go over two basic equations and some examples. So, why? Like I said, there's phone apps, pump charts, the old fashioned crank it up until the guy on the nozzle says it's good, or add a little more, or take it down a little bit. Well, all these methods can fail. You could forget your phone can die, the app can crash, you can lose a pump chart. Rough estimates, they work, but at the end of the day, it's always nice to know the math. You're not going to probably use it out on a call, or very often, but you need to know why you do things before you can kind of cheat the system and take the easy route. Like fire school or medic school or EMT school. You gotta learn the manual blood pressure before you can do the automated blood pressure. You gotta learn why we do things the way we do things before you can have the easy way. So some friction loss constants. This is kind of the more commonly used ones I picked. There's about six more than these. Those are booster lines and weird like inch and a half hose line and 3-inch hose line. Stuff that less common. So I didn't want to bog down with all the numbers. But future reference, there are more out there. And what these numbers are is for every 100 feet of fire hose, water going through it creates friction, and that causes you to lose pressure. So the smaller the hose, the more friction loss. So inch and 3/4 is pretty high. 2.5, nice easy 2, and your 4, 5, 6-inch, you're closer to a supply line. It's very little friction loss. And these are your standpipes. We're not going to touch on standpipes, but there's only a couple, and I tacked them on here. Like I said, there's more. That's more booster line, like 1-inch booster, 3/4-inch booster, like 3-inch, kind of between attack and supply line. I didn't go into those, but they're out there. So our first formula we're going to do, basic friction loss. Here's our total equation. Friction loss equals our coefficient that we had, and I should say, pause this real quick, write these down, take a picture, do whatever you got to do, because you're going to be needing these. Same with the formulas. But that's our coefficient, that's our magic number from the previous slide. Q is the flow rate in hundreds of gallons. So it's the flow divided by 100. So if you're flowing 200 gallons a minute, that'd be 2, or if you're flowing 400, that'd be 4. You get the picture. Flowing 450, it'd be 4.5. L is your hose length in hundreds of feet. So if you're doing a 200-foot length, it'd be 2, or if you're doing 250, it'd be 2.5. Get the picture. Short, sweet, to the point. Now the first one we're going to walk through. Find the flow rate, or find the friction loss for a flow of 300 gallons a minute out of 400 feet of 2.5 hose. So our coefficient is 2, because we're using 2.5-inch hose. That's our fancy number that we have to get our constant. Q of 3, because it's gallons per minute divided by 100. So, and length of 4, because again, It's our total length of hose divided by 100. So the math should look like that. Given an answer, once you square your gallons per minute, your Q squared, which when you multiply it out, you get 72. Next one. I think I did 4 or 5 examples of each, so now pause it, write it down, do the math. I'll keep walking through them, but take the chance, pause it, start working these out on your own, and we'll see if you got them right or what went wrong. So the formula should look like this. Our coefficient for inch and 3/4 is 15.5. Our flow rate squared, 150. Again, divide that by 100. Gives you 1.5 squared. And our L is 2.5, as it is 250 feet divided by that 100. Don't forget, you gotta square your flow rate. Should get you 87.2 for friction loss. And that seems really high, but again, when you're talking inch and 3/4, there's a lot of friction loss in that. Next one, 400 gallons a minute out of 750 feet of 6-inch LDH. So you're relay pumping, laying a long lay-in down a driveway, and you're really pumping into another truck, for example. The math should look like this. 0.05 for friction loss coefficient, because 6-inch doesn't have a lot of friction loss to it. Our gallons per minute are hundreds of gallons a minute squared, so 4 squared, times our length in hundreds of feet, so 7.5. Get your Q squared, should give you 6 psi. Seems really low, but again, 6-inch LDH really doesn't have a whole lot of friction loss to it. Alright, next up is elevation pressures. There's kind of two formulas here. Elevation pressure equals 0.5 times H. EP is elevation pressure, 0.5 is our constant, and H is our height in feet. This is good for terrain. So, you're working up a hill, or, you're down at the driveway slopes up and you're 20, 30, 40, 50 feet up a long driveway, that kind of thing. This one over here is elevation pressure equals 5 psi times number of stories minus 1. This is good for buildings. So where you get this is because the ground floor doesn't count. Ground floor, first floor is ground level, so there is no number for that one, as it is, on the same level as your engine. So if you're on the 6th floor, you subtract 1, get 5, and then you plug it in. We'll do a couple of these. And there's something to pay attention with this elevation pressure over here, the terrain one. I'm not going to tell you just yet. I'm going to see if you catch it. Alright, so calculate pressure loss for the hose line at the top of a 100-foot hill. You're parked at the bottom, crew's working up on the top of the hill. Pressure is our 0.5 constant times 100. Pressure loss of 50. Pretty simple, sweet, to the point. Calculate the pressure loss for a hose line on the 8th floor of a building. Our pressure is equal to 5 psi times our number of floors minus 1. Again, because the first floor doesn't count. So it's 5 psi times 7 floors, 35 psi. Short, simple math. Calculate the pressure loss for a hose line being used on the roof of a 30-foot tall building. It's like a storage shed or something, so we don't really have stories to work with. You probably could, because 10 feet per story probably gets you pretty close, but we know it's like a storage shed, so we know the shed is 30 feet tall in this case. Our constant, 0.5, times our height, gets you 15. Calculate pressure gain for a hose line at the bottom of a 75-foot hill. Elevation pressure, our constant, 0.5, times our height, 75, gets you 37.5 psi gain. Here's that little trick I told you. For example, you have to visualize with me with my pointer. If you're working at the top of the 100-foot hill, you got to push the water up the hill, which is where you get a pressure loss. But in this case, we're working at the bottom of a 75-foot hill. So your engine's up here on the road, and you're working down here 75 feet in a ditch, or, for example, or a spillway under a highway bridge or something. So really, you would gain pressure, not lose it. Because you're not having to push the water uphill, you're having gravity help you take it downhill. So if you were pumping this, and let's say you wanted 100 psi, at the nozzle, you would pump closer to, let me do the math here, to be perfect. We're going to call it 38, because there's no fractions in driver operator. You'd really have the pump set to 62 psi. Because you'd gain that 37, 38 just by going downhill. Whereas with our 100-foot tall hill, if you wanted that 100, you'd pump at 150 because you have to add that 50 psi to get the water up the hill. Other than that, thank you. I plan on doing, 1 or 2 equations at a time. Easy stuff first, difficult stuff later. If you didn't quite catch something or you need me to rehash something, let me know. And thank you for watching.